Hello, this is the video presentation from Group F for the assignment for Statics and Mechanics of Material, code KIB 1011. My name is Victor Hengjun Hong with the matrix number 25004013-1, and this is the analysis of barbell deadlift finish position. The purpose of this study is to understand the forces in equilibrium when weightlifting using a model we built to simulate a phase of weightlifting. The phase we choose to conduct our study on is the deadlift finish position. The position looks something like this. The lifter lifted the barbell until the barbell pole is the same level as his hip and pressed to his thighs. The spine is straight, the shoulders pull back, and the legs fully extended. Before we get into the details of our analysis, I'll go through some of the background theory involved in this analysis. The first background theory is static equilibrium. It means that a rigid body is at rest and not moving, and the net force of the whole free body diagram is zero. In the case of the deadlift, the lifter must exert the same amount of force in the opposite direction of the barbell weight to keep it still, in another word, hanging from his arms. The second background theory is force and moment. Since the barbell weight is a force acting downward because of the gravity, the lifter must exert force upward to pull up the barbell. As for moment, the lifter has to grip the barbell pole in the right place to gain more leverage on it. If the distance between both the hands and the hip joints is too far apart, the lifter has to use more force to lift it up. The third background theory is center of mass, referring to something like the main point of an object. When the barbell is lifted, the center of mass shifted to the barbell, so it is important to keep the barbell parallel with the lifter's midfoot. Since it is closer to the body, it can reduce the moment of the barbell, making the lifting action more energy sufficient. And even if the lifter has already reached the finish position, as you can see from this picture here, the barbell pole is still above the midfoot. It is to also reduce the shear force on the lifter's back, as excessive force can cause spinal injuries. Now on to the next section, I'll hand it over to my teammate.
Hello, my name is Ahmed, and for this slide, I'll explain how the physical model was built and why it was designed this way. So, to study the deadlift finish position, we created a simplified physical model of the human body. The goal here wasn't to perfectly copy human anatomy, but to represent the key mechanical elements involved in holding a barbell at the lookout position. The body segments such as the legs, torso, and arms were represented using aluminum wire. Aluminum wire was chosen because it is lightweight, easy to bend, and strong enough to hold loads without immediately falling. Each limb was constructed using a double strand wire, which improves structural stability and allows forces to transfer smoothly through the model. A chopstick was used to represent the barbell. This gives a clear horizontal reference and allows loads to be applied in a controlled, repeatable way. To prevent the model from tipping over, clay was added to the feet, increasing stability and mimicking the base of support provided by human feet during a deadlift. Overall, this construction allowed the model to remain upright and stationary, which is essential for applying static equilibrium principles. In this slide, I will explain how the experiment was set up and how equilibrium was achieved. Once the model was constructed, it was placed on a flat, horizontal surface to simulate the ground. This ensured the external factors like uneven support or surface tilt did not affect the results. Loads were applied directly onto the chopstick to simulate the weight of the barbell during the deadlift finish position. The loads were added gradually, allowing us to observe how the system behaved as the weight increased. The key requirement during the setup was that the model remained stationary, meaning there was no visible movement, rotation, or tipping. When the model showed no motion, we assumed the static equilibrium was achieved. This setup allowed us to isolate the effects of load and distance on stability without involving motion. acceleration, or dynamic effects. In other words, we froze the deadlift at the finished position and studied the forces acting on the exact moment. So on this slide, I will talk about how the forces and moments were analyzed. To analyze the system, free body diagrams were drawn for a barbell and selected segments. These diagrams helped identify all the forces acting on the system, including the weight of the barbell, reaction forces at the feet, and internal forces at the joints. To determine whether the system was in equilibrium, we applied the three fundamental equations of static equilibrium. Sum of force X equals 0, meaning all horizontal forces are balanced. Sum of Fy equals 0, meaning all vertical forces are balanced. Sum of M equals 0, meaning the sum of moments about a point is 0. Moments were calculated using the equation M equals F times D, where F is the force applied by the load and D is the horizontal distance between the barbell and the hip joint. This analysis allowed us to understand how increasing the load or increasing the distance from the hip affects the rotational demand. On the body, a larger moment means more muscular effort is required to obtain the position.
For this section, we'll be speaking about the results of our experiment. As you already know, we picked the last phase of a deadlift, so we wanted to see the internal forces at play that are involved at the level of the hip to keep the model stable. So for this section, the results, they are based on estimated values that we obtained from the physical model. What do I mean by estimated values? Well, the loads, we created them using clay masses that we started from 50 grams and we kept increasing in equal increments. Now, of course, we measured the entire bar, so this includes also the wooden bar and the clay. And we also ensured that at each end of the bar we added equal masses of the clay. So the mass would be like 20 grams for the clay on each end, and then the bar itself was like 5 grams. Right? We also kept the horizontal distance between the barbell itself and the hip joint at exactly 0.04 meters, and we kept it constant for all of the trials. We also, using these values, we calculated the hip moment using M equals force times distance. We calculated the force using mass times acceleration at acceleration equals 9.81. And we prepared this table, and as you already can see, as the force increases, the hip moment increases and the stability goes down. And what do I mean by this? At 50 grams, it was extremely stable. The hip moment was 0.02 Newton meters, and it was stable as if it wasn't holding anything. But as we go on, the stability went down. 150 grams, the stability that was observed, that it was slightly bending forwards, but it was holding up on its own. At 200 grams, it needed a tiny adjustment, external help, just for getting it to stand up correctly. And then at 250 grams, it, even with external help, it was not able to stay stable and it kept toppling forwards. So for this next part, I'll be talking about the center of mass positions of our model throughout this experiment, and which will explain why our model kept toppling forwards. So before we talk about why this was happening to our model, let's identify the center of mass without the load. It will almost be at the center, just above the hip pivot. It will be just there. Center of mass will be just above the hip pivot. So when you add the load at the 50 grams, we saw that the center of mass dropped downwards, but it did not go forwards. It only just went down. So our center of mass at the moderate loads improved the system balance because the lower center of mass makes it better to balance. But what we saw is that as we increased the load even more, beyond 100 grams, we saw that it started to cause an imbalance. So it shifted. So excessive loads, they shift the center of mass too far forwards. So if this was the model from a side view, the center of mass here would be with no load, and then it will drop down to here when there is a load, which would improve balance. And then with an extreme and excessive load, we will see that the center of mass will move forwards because the bar itself is heavier. So this will cause too much of a moment forwards, and the internal forces are just unable to keep the balance. So it causes rotational instability and causes the bending.
Hi, my name is Dayang Farzana, and now I'll be presenting the discussion section regarding the factors contributing to a more stable position, effects of bar length and mass, and limitations of the model. One key factor is the center of mass and base of support. A deadlift position is most stable when the combined center of mass of the lifter and barbell lies directly above the base of support, which is the area between the feet. Keeping the barbell close to the body ensures that its line of action passes near the midfoot, reducing the tendency for the system to tip forward or backward. Another important factor is the moment arm about the hip and lower back. The weight of the barbell creates a moment above these joints, and the bar is held closer to the body. The moment arm is smaller, which reduces the external torque acting on the hip and lumbar spine. As a result, less counteracting muscle torque is required to maintain equilibrium, making the position more stable and mechanically efficient. Stability is also influenced by joint alignment and force distribution. In a stable deadlift position, the joints are aligned so that ground reaction forces act vertically through the body. This reduces shear forces at the joints and allows forces to be distributed more evenly, improving balance and reducing unnecessary joint loading. Next, I'll discuss on the effects of bar length and mass. When bar length is increased, the bar has a greater moment of inertia, which makes it more resistant to rotational disturbances. This improves rotational stability, especially against small lateral movements, although it also requires more precise positioning to avoid uneven loading. Increasing the mass of the bar increases the downward gravitational force acting on the system. To maintain equilibrium under heavier loads, lifters naturally adjust their posture by keeping the bar closer to the body. This shortens the moment arms about key joints and helps minimize the torque that must be countered by muscles. Finally, the model used in this project present these following limitations. Firstly, the model simplifies the human body into rigid segments connected by idealized joints and does not explicitly represent muscle forces. This limits its ability to accurately reflect internal joint loading and individual muscle contributions. Secondly, the model assumes static equilibrium, whereas real deadlifting is a dynamic movement involving acceleration and inertial effects. As a result, peak forces experienced during the lift are not captured. Lastly, the model is limited by planar two-dimensional representation and simplified scaling of body segments and mass distribution. This restricts the analysis to qualitative insights rather than precise biomechanical predictions. Despite these limitations, the model provides a useful framework for understanding force and moment balance in the final phase of the deadlift.
For the conclusion, I'll summarize what the study shows and why it matters. In this study, the deadlift finish position was analyzed using principles of static equilibrium. A simplified physical model was developed to represent the lifter barbell system, allowing forces and moments to be studied in a controlled and systematic way. The analysis shows that when the barbell is kept close to the body, the horizontal distance from the hip joint is minimized. This results in a smaller moment, making the position more stable and mechanically efficient. On the other hand, increasing the load or allowing the barbell to move further away increases the moment, which reduces the stability and increases strain on the body. Although the model is simplified and does not perfectly represent human biomechanics, it effectively demonstrates how forces balance, moments on arms and center of mass influence deadlift stability. Overall, this project reinforces the importance of proper barbell positioning in maintaining equilibrium and reducing injury risk during deadlift.